Welcome to this masterclass on one of the most fundamental algorithms in modern computing, gradient descent. To understand how artificial intelligence learns, we must first travel back to the roots of statistics. Since the 18th century, mathematicians like Adam and Legendre and Carl Friedrich Gauss were obsessed with a problem: how to find the best fit line through a cloud of data points. This is what we now call linear regression. Imagine you are looking at data from the real world, perhaps the relationship between the square footage of a house and its price. We have a set of points, and we want to draw a line that predicts the price for any given size. In statistics, we define this line as y equals mx plus b. But how do we know which m, the slope, and which b, the intercept, are the absolute best? This is where the concept of the cost function comes in. The cost function, often denoted as j of w comma b, is a mathematical way to measure how wrong our model is. The most common version is the mean squared error. It takes the distance between our predicted line and the actual data points, squares them to remove negative signs, and averages them. If our cost is high, the line is a poor fit. If it's low, we are close to the truth. In a 3D space, this cost function looks like a valley or a bowl. Now, here's the challenge. In the past, with small datasets, we could use normal equations to solve this using linear algebra. But in the era of big data, where companies like Google or Meta process billions of parameters, solving these equations directly is computationally impossible. We need a way to walk down the hill of the cost function to find the lowest point. This iterative process is called gradient descent. Think of gradient descent as being a hiker lost in a thick fog on a mountain. You can't see the bottom of the valley, but you can feel the slope of the ground under your feet. If you want to get to the bottom, you take a step in the direction where the ground slopes downward most steeply. In mathematics, this slope is the gradient, a vector of partial derivatives. The formula is elegant. We update our parameters by subtracting the gradient multiplied by a learning rate denoted by the Greek letter alpha. The learning rate is a crucial hyperparameter. If it's too small, the computer will take forever to learn, moving in tiny microscopic steps. If it's too large, the algorithm might overstep the bottom, bounce back and forth, and eventually fail to converge or even explode to infinity. There isn't just one type of gradient descent. In batch gradient descent, we look at every single data point before taking one step. While precise, it's slow. Then we have stochastic gradient descent, or SGD, where we take a step after looking at just one random data point. It's noisier, like a drunk person walking down a hill, but it's much faster and can help escape local minima, small dips in the mountain that aren't the absolute lowest point. Today, gradient descent is the heartbeat of deep learning. From the transformers that power ChatGPT to the computer vision in self-driving Teslas, every single one of these models uses a variation of this algorithm, such as Adam or RMSProp, to minimize error. By understanding how to descend this mathematical mountain, we've enabled machines to learn from experience, turning raw statistics into the engine of the 21st century. References: 1. Deep Learning by Ian Goodfellow, Yoshua Bengio, and Aaron Corville. 2. Introduction to Statistical Learning by James, Witten, Hastie, and Tibshirani. 3. Pattern Recognition and Machine Learning by Christopher Bishop.